Yes, we can.
Yeah, okay, thank you. So yes, I'm going to talk about the research that we're doing in my group, which is in the context of first principles kinetic modeling for catalysis and material science. So the motivation is mostly catalysis, which is important in the chemical industry. It's at the heart of the chemical industry because, of course, several of the conversions that we need to do from reactants to products need to be accelerated with the use of catalysts. And in fact, in chemical synthesis processes, most of these processes employ solid catalysts, heterogeneous catalysts. It is estimated that catalytic processes are contributing to something between 30 and 40% of the global GDP. So this shows how important catalysis is. And in terms of the practicalities of it, what we need for a dream catalyst is to exhibit high activity, high selectivity, and high stability so that we can accelerate the chemical reaction towards the products that we want and not byproducts. And also the functionality of the catalyst has to remain stable for long time scales so that we don't need to stop the chemical process every so often and replace the catalyst. So all of these things are quite important from a practical standpoint, but the question of finding this dream catalyst is not trivial. So what we're doing in my group, we really adopt this rational catalyst design paradigm. So we use computations, theory, and simulation to try to inform practitioners in industry on what types of materials might be potential candidates, promising candidates for certain applications. So we aim at, first of all, getting some fundamental understanding, and second, aiding in the design, the engineering of catalytic materials. So this is our aim. How do we do this? We use electronic structure calculations, mostly density functional theory, to investigate the electronic structure of materials, calculate absorption energies, calculate the energies of reaction and also activation energies. And we do this for several different geometric structures of the materials, because in practical applications, it turns out that several of the reactions are structure sensitive. So they occur with different rates if the material is exposing different facets like the 100 or the 111 that you see in this cuboctahedral particle. So once we have this information from density functional theory, we essentially compile large data sets of the catalytic pathways that are possible for a certain material. So we investigate essentially the chemistry, the underlying chemistry of our catalytic process. So we calculate rates of reactions from transition state theory, and then we give these rates as input to kinetic Monte Carlo simulations primarily. We are also developing other approaches for kinetic modeling, but we mostly do kinetic Monte Carlo. And using this kinetic Monte Carlo framework, we are able to estimate catalytic performance metrics like activity, how many molecules are produced or consumed per unit time per site, selectivity, how much of the desired product we get versus byproducts. And then, of course, we can make statements about the stability of the catalytic material over long time scales. So this is the overall framework of these computational catalysis studies across different scales. And in the next few slides, I wanted to just summarize the method development activities and some of the applications that we are working on. Then I'm going to talk about some specific examples. And finally, I'm going to touch upon opportunities for collaboration. So we are developing kinetic Monte Carlo methodologies and software. So we have pioneered this graph theoretical kinetic Monte Carlo approach, which allows us to take into account complicated reaction events on catalytic surfaces. These surfaces are represented as lattices, and then These lattices are essentially represented as graphs in the framework. And we also represent the binding configurations and the reactions as graphs, so we can have flexibility in terms of the representation of the reactions, but also the representation of lateral interactions between adsorbates on the surface. So because on the surface we are operating under condensed phase conditions, we may have attractive or repulsive interactions between the adsorbed molecules, which have been shown to exert an influence on the rates of the reactions. We are developing software, so we have this Zacro software, which is already in use by hundreds of groups worldwide. And one of the recent projects aims at advancing these kinetic Monte Carlo approaches to try to exploit emerging and massively parallel architectures. So one of the most recent projects on the methodology development and software development has to do with the implementation of the so-called time warp algorithm, in which we break a large domain into subdomains. Each of the subdomains is assigned to an MPI processor, and then all of the processors have to communicate with each other to solve the problem. It is highly non-trivial because this decomposition can lead to causality paradoxes. And of course, there have to be some rollbacks and resimulations and certain communications that will resolve these causality paradoxes. So this is done using the time warp algorithm. And we actually have a webinar that if you're interested, I can send you the link to learn more about this. In addition to that, we're coupling the kinetic Monte Carlo with higher level approaches, larger scales, and also with smaller scale approaches. Of course, we're already doing this because we use DFT to calculate the rates, but the point here is to try to do it in a seamless way and efficient as well. So this is in the context of this European project, REACT Pro, that we are aiming at developing software that can do this coupling and linking in an efficient and validated way. In addition to kinetic Monte Carlo, we are also formulating novel methodologies that go beyond kinetic Monte Carlo, which is on the one end of highly accurate but very expensive calculations, but also go beyond the mean field approaches, which are very efficient, but not high fidelity. They're not as high fidelity, they're not accurate. So we have been developing approaches that essentially are based on ideas of embedding a cluster of sites into a mean field. And then from that, we take into account the lateral interactions explicitly inside the cluster and in a mean field sense when it comes to coupling what happens on the cluster with the mean field. And of course, there are some corrections that need to happen there. So we have benchmarked the methodology, and I will show you in a moment how well it does. So in terms of the applications, we're focusing on quite a lot of different reactions that are of interest in the fields of chemical engineering, sustainable chemistry, etc. So one of them is emissions control. Try to find active catalysts for clean air. So we have investigated chemistries like CO oxidation, NOx reduction on materials like gold nanoclusters, platinum, palladium, etc. We're looking into biomass as a sustainable feedstock for fuels and chemicals. Some example reactions that we're looking into are shown here. So hydrodeoxygenation on single copper atom dispersed on molybdenum disulfide. We're also looking into CO coupling reactions and CC coupling reactions on gold-based catalysts. These are gold facets, but also single atom alloys. So these single atom alloys are basically alloys of two metals in which one metal is at a very small minority. So we have atomically dispersed minority metal sites onto a host that can be gold, but also copper, silver, etc. So this is the project I just mentioned. So catalysis on highly dilute alloys at the single atom alloy limit. So we're looking into a lot of reactions again. Some of them are hydrocarbon activation, like in the context of methane valorization, and also how to overcome CO poisoning effects on these catalysts. So in the next few slides, I'm just gonna show a few results from some of these studies, just to make the point that these methodologies are actually useful in trying to understand these systems, and we have obtained high accuracy, good agreement with experiments. That's how we measure accuracy anyway. So one of the systems is this CO plus oxygen titration. It's CO oxidation on palladium 111 surface. And this was motivated by an experiment that was trying to understand the difference in the orders of the reaction with respect to oxygen coverage at high versus low temperatures. So you can see these orders here. So these are the experimental orders. First order reaction kinetics at low temperatures, half order reaction kinetics at the high temperatures. And we see that with the simulation, we get a pretty good agreement, right? Simulation results versus experimental results. What motivated the study was this puzzling half-order reaction at a high temperature. In the experiment, it was attributed to island formation, but then if you have islands at the high temperature, why don't you have islands at the low temperature? So this was the question that we tried to answer, and it turns out that it's not because of island formation that you have half-order kinetics at the high temperature, it's because of the effect of lateral interactions between the adsorbed species. So some other metrics that we can calculate are activation energies, which again, we see a good agreement with experimental data, and also orders with respect to gas CO pressure. So this was one system that actually shows that high fidelity kinetic Monte Carlo simulations can indeed give insight that leads to alternative interpretations of experimental data, which are not trivial. Another more complicated system that we have looked into is CH activation. So here, we're simulating a single atom alloy surface, and this is platinum copper in particular. So this shows the lattice representation as a graph. These are the elementary events that we can have. So we essentially have the CH activation events, dehydrogenations, all the way up to carbon and hydrogen on the surface. And this shows the temperature program desorption spectra, which are in agreement with experiments. So here I only show the theoretical results, but the peaks and the overall behavior of these curves is in excellent agreement with experiments. Bottom line is that if you use platinum to do CH activation, you can do it at very low temperatures. However, eventually you're going to coke the material, so your catalyst will become inactive. This is not shown here, but we have looked into the structure of the surface at these high temperatures, and indeed you don't, so you block the catalytic sites with carbon. If you do this with copper, you're going to get the CH activation happening at high temperatures. So this is not a good catalyst because it's not active at low temperatures. And the single atom alloy, which is here, this platinum copper single atom alloy, can do the CH activation at intermediate temperatures. And we have also seen that it doesn't coke. So effectively, it exhibits the best of both worlds from platinum and copper. So the last example that I wanted to show is these novel methods for kinetic simulation. So what this shows is a sequence of approximations. Each one of these curves here is an approximation, and with the exception of the red points here, which are the kinetic Monte Carlo data. So the red is the accurate kinetic Monte Carlo. The black here is the mean field approximation, which is quite inaccurate. So what we show is the activity, the turnover frequency, the activity of the catalyst at different conditions. And we see that as we go down the list of different approximations, in the end, we have this type of approximation here, which has almost exactly the rate predictions as the kinetic Monte Carlo. So we see that with the hierarchy of these approximations, we can get to a situation that we converge to the accurate kinetic Monte Carlo results. And if we look into the computational cost of these things, we see that the most accurate approximation is 10 to the 5 times cheaper than kinetic Monte Carlo. So this shows that we can do kinetic simulation at a much lower cost than kinetic Monte Carlo with a minimal loss of accuracy, as we see over here. Of course, these are early stages for these approximations, so they're valid for simple systems, one site type, one absorbing species. So we're looking into expanding these simulations to more complicated systems in the near future. So potential topics for collaboration could be from the methods development side. We are always interested in more accurate ab initio methods for better parameterization of KMC models, because of course all of these results, as the previous speakers noted, they depend on the functional, they depend on the method. So some of the open questions, of course, have to do with more accurate functions, but also things like semi-infinite slabs. Also larger particles, so try to take into account these, calculate the binding energies and the formation energies of transition states for these two situations, and also in the presence of weak interactions. Also accounting for solvation. Right now, all the calculations, or most of the calculations that we're doing in my lab, assume dilute bulk phases, so ideal gases effectively. So accounting for solvation is of interest in practical situations. So that would be of interest if anybody is developing methods like that. Also, another thing is the thermal contributions of low frequency modes. This is a bit of a problem for harmonic transition state theory, because sometimes we have adsorbed species that have very low frequency modes, right? So numerically, if we try to calculate the vibrational frequency for these, we might get something which is numerically imaginary. And in any case, we know that even if we have something which is real, but very low frequency, like 5, 10 wave numbers, we know that using harmonic transition state theory would not result in a very accurate rate. So maybe, I don't know if anybody is developing methods to tackle these problems, but maybe if we have more advanced parameterization methods that go beyond harmonic transition state theory, or maybe another solution would be phase space averaging with machine learning potentials or something along these lines. So these would be of interest to us if anybody is developing such methods. From the application side, we're always interested in having people using or benchmarking our kinetic Monte Carlo methods, and of course software Zacros. Kinetic Monte Carlo on large systems, I believe, is going to be the way of the future, if you wish. So we're talking about billion site type of simulations that might be of interest if we're looking into material science problems like dislocation effects or catalyst reconstruction effects, etc. So we now have implemented the time warp algorithm in Zacros. So it's the first time that this has been, as far as I know, that this has been implemented in a general purpose kinetic Monte Carlo software. So we're always looking into collaborating with researchers who might be interested in that. And finally, more advanced catalytic processes like photocatalytic or electrocatalytic processes. So maybe we can talk about this with Alex and Jochen. I found some their presentations very interesting in that front. So for more information, you can look into these websites. This is the website of the group, and this is the website of Software Zacros. So with that, I think I'm out of time. So thank you for your attention. And if there are any questions, we can discuss.
Alex has a question about error propagation.
Yeah, Michael, so basically it's kind of very common to also what we are doing in a similar way, but we know that you combine lots of things in exponents through this multi-scale modeling. And so I'm wondering, how do you deal with error propagation in this simulation in order to achieve such accuracy? I mean, for example, in our simulations, we rarely think about real quantitative comparison. We kind of we think about mechanisms, and we are lucky if it is semi-quantitative. But say one is always, as you say, conscientious about the fact that actually, say, barriers and all of these rates, etc., they are exponential in many ways. So it's any small error can lead to quite. You need to be lucky either with compensation of errors, or you need to be really, really very accurate. So what do you say?
Yes, so this is true. There is this problem, and of course, it's magnified by the exponential relation between activation energy and rate. So we don't claim, so this is one system that we can get quantitative predictions, but something that I didn't explicitly say, but you can see it from the plot, is that if you look into the low activation energy and the high activation energy range, the switching point is overestimated in the simulation. So this is one example that shows error in the DFT that is propagated and shows up in these predictions. We do pretty well in the other metrics here, but the point is, as you said, we don't claim that we necessarily have quantitative accuracy or that we are interested in quantitative accuracy. When we get it, that's really good news, excellent. When we cannot get it, at least we have seen that we can get useful information in terms of the mechanisms and the different, for example, the different pathways that are active under different conditions, or the different qualitative behaviors like this. If we are overestimating the temperature for switching, or like the pressure for different mechanisms to kick in, that's fine. At least we can get some qualitative statements to be made that allow us to explain experimental results. We have seen this quite a lot when we try to match temperature program desorption data like these, or really temperature program reaction data with DFT. And in some cases, we've actually done calculations, and Roman can talk a little bit more about this. I think he's online, one of my postdocs in the group. So we've done calculations with different functionals to try to see which ones might be giving us a better agreement with experiments. And then we discuss, in our paper, we discuss the mechanisms. We say that here is what we get with the functional that seems to be the most accurate for this process. And here is what we get with others. And here is why we think that these are inaccurate. Right? There is always a way to benchmark things in detail when you have such experimental data as temperature program desorption and reaction.
But say on this temperature program desorption, also for some of these bigger molecules, say entropic effects should be playing some role in your free energies, right?
Yeah, that's for sure the case. We have not really worked on very large molecules. So the largest molecule that we've worked on, or the chemistry with the largest molecules, is the methanol coupling, in which the largest molecule would be this methyl formate and these hemiacetals that we have. So this is it's a class of molecules that have like these CO-C bonds. So you have two methanols condensing and giving you these molecules. So we didn't have too much of a problem there, but with collaborators in Harvard, they wanted to go even further, right? So go with like ethanol or propanol, and they have had quite a lot of problem with that. So that's why one of the potential topics for collaboration is this one. So these thermal contributions.
Yeah, Michail published some paper with Dario, a couple of papers before, showing that you have even quite strong effects even for water molecules. from entropic contribution for this form of desorption, if you want to predict the the energies and peaks correctly. So we also looked a little bit at that for various molecules. There are indeed very big effects, even for quite small molecules for rotation and vibrational entropy, which needs to be included in many